Okay, I'm going to do a quick review of the stellar evolution notes. Let's start off with leaving the main sequence. Now, a common misconception is that we see these stars, being born and dying and going through these different stages. We don't, in fact. We actually just instead see examples at every possible stage. I call this the target theory, Walmart theory, whatever you want to call it. It's like if you went into a Target, you could see every stage of a human's life within a Target or a Publix or something like that. No, we use the term evolution because it's changed during the lifetime. Evolution on our planet occurs slow biologically, but the evolution of a star actually is much slower. Now, the real reason that stars evolve or change is because they're trying to balance hydrostatic equilibrium, gas pressure or energy pressure out with gravity being pulled in. And when a star is balanced like that, it's very happy on the main sequence. When a star starts to become unbalanced, it no longer stays on the main sequence. Stars start to swell, temperature increases, swells up, and then cools because it gets too far away from the core, therefore recovers equilibrium, and this goes on for years and years. A decrease in the temp causes a decrease in pressure, causing the star to contract, and when it contracts, it thereby heats up again, so it's a cycle. Now, stars like our sun, we usually mention our sun because it's the star we know the most about. Their fuel in the core regions start to change. Early on, if you can see up here, most of the core region, which is denoted by the dashed line down, right, if you see here on this one, is hydrogen, a little bit of helium. Over time, as the proton-proton chain continues, helium-4 continues to be built up. This means less of the hydrogen is in the core. And after about 10 billion years, you have a very small amount of hydrogen in the core and a lot of helium. Now, that doesn't mean the star is, doesn't have hydrogen. If you look out here, most of the star is still hydrogen. So because helium is a larger atomic nucleus, has 2 protons, Coulomb's law will repulse it even harder, so it takes a much higher temperature to fuse helium, and that would be 10 to the 8th, which is 100 million K. Our star does not get that hot until it starts to go through some changes. But because helium is a bigger atom as well, it's more dense, and it therefore will settle in the core, the very central of the core region. This basically makes the star a 2-core system, this middle part being the helium, and at this point it's called the helium ash because it's not burning, it's not fusing, it's just kind of sitting there and accumulating and building up. This pushes the hydrogen out to what we call hydrogen shell burning. Now, fusion, the proton-proton chain, is still going on in this layer here. But there's nothing happening in this part. This causes the star to swell because, going back to this pushes this region out here. Well, then this, in turn, will push these other regions out, the radiative zone, the convective zone. So we'll start to enlarge the star, and at this point it leaves the main sequence and it heads to the subgiant branch. Now, the subgiant branch is basically right off of the main sequence as it's swelling up due to this increasing helium core, the helium ash. Keeps getting larger and larger, from 7 to 8 to about 9 or so, because helium keeps building up, and it just keeps building up in vast quantities, and this keeps making the star push out the hydrogen core and swell up in general. And it does rapidly, I hate to say rapidly, it takes about 100 million years. It does drastically swell up and become larger. Until we reach a point in position 9 up here, which is called the helium flash. Now, the helium flash is a point where the star starts to be able to fuse helium. This is called the triple alpha process, and it's called alpha process because the hydrogen or helium is the alpha particle, especially in radioactive decay. Helium plus another helium is going to make all this. End-all result being carbon. So that becomes important. Now, what happens with the helium flash? Pressure outside remains relatively the same, but temperature increases. This causes the core to expand. As a result, overall size of the star decreases. Well, as it gets smaller, it gets hotter, and this will allow the required temperature to start fusing helium with the triple alpha process. Looking at the HR diagram, you can see that the helium flash actually occurs here. When the star contracts and gets hotter, it's hot enough to fuse the helium, and you can see it moves to the left of the HR diagram, and it'll be at a variable state for some time, tens of millions of years. And it'll kind of swell up and get larger radius-wise, and then it'll kind of contract and get hotter, right? And it'll kind of dance along this horizontal branch for a while. At this point, as helium's fusing, the triple alpha process, carbon starts to build up in the core, just like helium did build up in the core. And this will make the star start to swell up again and go from position 10 to 11. Here you can see the carbon ash building up. Now you have the helium pushed out and the hydrogen pushed out, and then all the other radiative zone and convective zones are pushed out as well, and this makes the star get to its largest point. If it could get hot enough, a star like ours, it would start to fuse carbon, but it won't. It needs about 600 million K to start fusing carbon effectively into oxygen. It kind of shows, I really like this diagram, but protostar hanging out over here on the HR diagram, or off the side of the HR diagram. This is supposed to be the main sequence here. A little away. I don't really like that diagram. Let's move on. Alright, so at this point, when it's at the asymptotic red giant stage, the burning becomes completely unstable. It starts this series of what we call helium shell flashes, and basically making the outer layers of the star pulsate. So, and at the peak of each pulsation, the temperature drops enough, and this is important, that electrons can recombine with nuclei. When that occurs, photons are released, and this photon pressure is the last little push that the outer layers of the star need to separate from the star. And we call this separation of the star's outer layers a planetary nebula. So they start to puff away over a few million years, and typically in bursts. And that's a good example of this is this one, right? This is an early burst, and then these are a little bit later inside of here. They shine because the core of the star, which becomes the white dwarf, is still really hot, so it excites the gas around them, and makes them emission nebulas. This graph shows that as time goes on, the star will swell and contract and swell and contract, and it starts getting to a ridiculous point, right? It swells up to over 7 radii, and then it'll contract down to less than 5. That's a significant amount of contraction and swelling. So the star becomes very unstable. And the envelope itself will eventually fade away because it's, basically puffed off with force. So it is moving away from the white dwarfs at all times. So anytime you see a planetary nebula, it won't look like that in a few million years. I mean, it'll look like that for our entire lives, but that's a very small amount of time astronomically. So central star eventually fades and cools. Envelope eventually disperses into interstellar space. And at some point in the future, it will basically, we won't even know that a star was there, except for that last stellar remnant. Now, last stellar remnant is the carbon core, and we call this the white dwarf. It's very small relative to a star. It's about the size of Earth, which is really small, but it has about half of the mass of the sun because it was the core. This makes it ridiculously dense, of course. Although it's ridiculously hot, it's not very luminous because it's so small. So it puts it in a weird spot on the HR diagram, which is that lower left. Stars of lower mass will have helium white dwarfs because they'll never get hot enough to fuse helium. Stars larger than the sun but smaller than 8 solar masses form neon oxygen white dwarfs because they're able to fuse carbon for a while. So the core of the star will be neon and oxygen. They do eventually cool at some point to yellow and then to red, and then they kind of disappear because they turn black, right? At least this is theoretical because it'll stop emitting light, and it will therefore be black. And we believe that'll take somewhere around 1 trillion years. We don't know because the universe is not that old. So every white dwarf that was ever made is still out there. So even though it cools, right, gravity's not allowed to compress it any further because of something that we call electron degeneracy. And electron degeneracy is due to the resistance of electrons being pushed together. Now it's basically electrons don't like each other, so like charges repel, and that's what holds the core of the star together. This shows pictures of some distant white dwarfs within this globular cluster. What you should notice is that there's no planetary nebula around these, so it denotes that they're not new white dwarfs. Stars more massive than the sun are able to burn their fuel or have to burn their fuel at a faster rate to maintain hydrostatic equilibrium, and that's because as a star is larger, right, gravity is stronger, so to maintain that pressure out, it has to burn at a hotter rate. An example of that is an O-type star that will live about 20 million years on the main sequence. That's a very short amount of time for a star. Unlike the sun, stars are more massive. They basically move horizontally. So if you look at this star, it doesn't do like the little dance like our sun does, right? It goes straight over to the left, or to the right, sorry. It maintains the same luminosity. If you look on this scale here, maintains the same luminosity, but what you notice is it's decreasing in temperature because it's still swelling up, right? Because if you look at this line right here, you have a 10 radius star, 10 solar radius, but as it goes over, it's getting larger and larger and larger and larger, but it's maintaining its luminosity because it's getting larger and larger and larger, but the temp goes down. CNO cycle, you don't need to know all this stuff down here. It is the fusion process that larger stars use. It's more energy, it produces more energy than the proton-proton chain. That's what the PP is here. That's really what it's showing is energy yield versus over temperature, right? So at low temperatures, the proton-proton chain is more productive, right? But once you reach past about 16 million, CNO produces more energy per kilogram. So it's the fusion process that large stars use to maintain hydrostatic. Let's see. Just went over the massive star real quickly. I just went over all of that. And we can observe the time that takes for, or how old globular clusters or a set group of stars that happen to be close to each other are based on the HR diagram. So in this case, if you look up here, this is a very young globular cluster. It has blue stars still, and if you remember, they only last about 20 million years, so that means this is very young. Also, the red dwarfs have not even settled onto the main sequence. They're still in the protostar stage. Now, if you, inversely, this goes down and then up like that. Inversely, if you look at this, this is an older globular cluster because all of these stars have already fallen off the main sequence. You have white dwarfs showing up, you have lots of red giants and red supergiants, and the horizontal branch is very evident. And the only stars still in the main sequence are G-type stars, which are like our sun, so it's about 10 billion years old. Binary star systems can evolve in a couple different ways. If they're very widely spread apart, and I put about 1,000 solar radii, they'll evolve completely independently. One will turn into a black hole, one will turn into a white dwarf, and there's no worries whatsoever. However, if they're closer, it starts to become an issue. The Roche lobe of a star is the area of gravitational influence around the star, and it's a sphere. And our star, for instance, our Roche lobe of our star goes out past the Oort cloud. But in a binary situation, two of these stars will be essentially connected at one point. And that point that they're connected at is called the Lagrangian point. And this is basically a point of gravitational neutrality between the two stars. So if you're here, the blue star is going to dominate it. If you're here, the red star is going to dominate it. But that point right there is the gravitational neutrality between them. It's also the center of mass between the two stars. If you have a close binary system, this is what happens. You have a detached binary up here, which means they're completely not attached, right? A blue star and a yellow star. They're living their lives. Everything's hunky-dory. Over here, you see it's turned to a semi-detached binary because the blue star has went through red giant, and because it's swelled up to such a point that it passes the Lagrangian point, it now becomes gravitationally bound to this star. So it basically eats this yellow star ends up eating the mass off of the red star. This will cause what we call a contact binary because as this star gains mass, it will go into red giant at a faster rate, and then you have them basically touching, two different stars touching each other, evolving together at this point. Basically just what I described. If you want to pause it, feel free. Last thing we're going to talk about is what's called algal evolution. And algal evolution is named after a star named Algol, right in the star system. That when we looked at this data, we were very confused by it. It says it has a 3.7 solar mass blue star that's on the main sequence and a 0.8 solar mass red giant. That doesn't make sense because this star should have been long dead if this star is already in red giant. This is smaller than our star. So what happened is a binary system transferred large amounts of mass and changed the type of star. So stay with me up here. Star 1 is blue, star 2 is red, main sequence star, probably like a red dwarf. This star will live its life, start to swell up and die much earlier than the other star. But as the mass transfers over to this star gets bigger. Here it was red, now it's yellow. The star gets bigger, and it's going to evolve at a faster rate, burning more fuel. Now you'll notice the Roche lobe of this star has decreased because it's lost mass. If it's lost mass, it's lost gravity. This star now is a blue star, because it's gained so much mass that it's able to churn out, a blue color, and therefore kind of be inverse to what you normally see, a blue star and a red giant. That doesn't really make a lot of sense. But that's because it's passing this over. So anyway, hopefully that's helpful to you. That's stellar evolution, and I guess study up.